Hi, I'm Professor Goins, and welcome to the Math Professor's YouTube channel. If you find the content useful, please consider giving us a like, a comment, share our videos. Most importantly, give us a subscribe. At this point, we're a very small channel. We have a very low number of subscribers, so any interaction you can give us will help us grow. So again, please consider giving us especially a subscribe. Okay, so for this video, I'm going to take a look at the integration by partial fractions technique, and I'm going to call this part 1 to be followed up by numerous follow-up videos. Okay, integration by partial fractions part 1 is going to consist of the following. The integrand is a proper rational function, and the denominator consists of non-repeated linear factors. I'll elaborate on what all that means here in a moment. But what I want to do first is I want to do a quick algebra exercise, okay, to get things motivated. All right, let's say I take 2 divided by x plus 1, and I want to add 3 over x minus 2. All right, in order to add those, in order to add fractions, we have to have common denominators, and of course the least common multiple of these denominators would be their product. This first fraction already had a factor of 2, so we need to have that factor of 2. I included a factor of x minus 2 in the denominator, so I have to do the same to the top. Over here, we already had a factor of 3. I introduced a factor in the denominator of x plus 1, so I have to do the same thing to the top. Since the denominators match, of course, I can add the numerators. Distributing the 2 and the 3 through the grouping terms here, we would have a 2x and a 3x giving me a 5x. And then I would have 2 and negative 2, so negative 4 plus 3 giving me minus 1 all over x plus 1 times x minus 2. So this expression right here is equivalent to this expression right here. Well, what that means then is that suppose I had an integral where this was my integrand. Well, since this expression is equivalent to this expression, the integrals would be the same. This is a challenging looking integral. This one is pretty trivial once you know about the natural log. This would be 2 log x plus 1, 3 log x minus 2. So this one would be easy. This one, not so much. So here's the question. Suppose I give you, suppose we start with one of these, right? What I want to figure out is, how do I go from here to here? Clearly, we can go from this expression to this expression by just adding the fractions together, by adding the rational expressions together. But how do I go in the reverse direction? And that's going to be the content of this current video, is how do I go from this expression, if I start with it, to this? All right, so let's go through an example illustrating how we accomplish that. All right, so let's say I've got the following integral. 1 divided by x times x plus 3. So how do I integrate that? Well, here's what I'm going to start by doing. I'm going to write what I'm going to call the generic expansion. Meaning, I take the integrand and I want to figure out what fractions did I add together, what rational expressions did I add together to get this. Well, the motivation comes from this first example, that if I started with this, it looks like I would have had the following possible denominators, an x plus 1 and an x minus 2. So I probably added something with over x plus something over an x plus 3. Now, certainly I'm going to erase this, but certainly it doesn't make sense to say, well, I could have had a denominator of x minus 4, because when I find the least common denominator between these, I'm going to have a factor of x minus 4, but that doesn't appear over here. So the only possible denominators would be each factor that I have in the original expression. Excuse me. What I don't know is what the numerators were. It could have been, maybe it was a 2 and a 3, maybe it was a 1 and a 4, maybe it was a 1/2 and a 4/5. I don't know. So what we'll do is we'll label those as generic constants, where we have to solve this equation for a and b. So I set up my generic expansion, and from this, once again, I have to solve for a and b. Here's how we do that. From the generic expansion, I'm then going to move on to the coefficient equation. And the way I come up with the coefficient equation is I take the generic expansion and I'm going to eliminate all the denominators. So let me just rewrite that first. Now, if I want to eliminate all the denominators, so I want to eliminate this one, and this one, so therefore what I'll do is I'll multiply the entire equation by the denominator on the left-hand side of the equation. And again, this is going to get distributed. I guess that doesn't show up very well. Switch to a different color. I'm going to distribute this expression here to the first term, second term, and the third term, right? When I distribute this over here, everything cancels in the denominator, leaving just whatever the numerator is, meaning a 1. When I distribute to here, I'll get this factor of x and this factor of x would cancel, giving me a times x plus 3. When I distribute to this term here, the x plus 3's are going to cancel, leaving just the factor of x along with the b. So I get this equation right here. This I refer to as the generic expansion. This I refer to as the coefficient equation. Now, the way I'm going to use the coefficient equation is the following. I'm going to choose values of x. So this equation has to hold for every value of x. So what I'm going to do is I'm going to pick kind of convenient values. I can really pick any x value since it holds for anything. But notice there's a couple different x values that I plug in there that are going to end up doing a nice thing for me. Meaning if I plug in x equals -3, that's going to zero this out, and then I'll have one equation with one unknown. Same thing if I plug in x equal to 0, that would zero this out, and that would give me one equation with one unknown. Okay, so again, let's choose some convenient x values. If I say let x equal to -3, and I plug that into this equation, I would get 1. I get 1 is equal to a times -3 plus 3 plus b times -3. Well, of course, this term here is 0, and then I can just divide by -3, and I find out that the coefficient b has to be -1/3. So in that generic expansion that I have up above, I now have the value for b. Very well for me. There we go. Let's go ahead and choose the other convenient value for x. Let x equal 0. If I plug in x equal to 0, I'm going to get 1 is equal to a times 0 plus 3 plus b times 0. And of course this term is 0. This would be 3a. Dividing by 3 gives you a is then equal to 1/3. So now what we do is we go back to the original question, is what is the integral of 1 over x times x plus 3? Well, what we just found is that that integrand is equal to this expression right here, where a and b are the numbers we just found, meaning 1/3 and negative 1/3. And these are both easy to integrate. Okay, this would give you 1/3 natural log absolute value of x minus 1/3 natural log absolute value x plus 3 plus c. So this right here would be the antiderivative of that expression. Okay. Now I'll do another example for case 1 where the denominator consists of non-repeated linear factors. But you could imagine if I had a third factor here, or a fourth, fifth, sixth, it's going to work out the same way, where each factor in the denominator is going to contribute to one expression in the generic expansion. And then after I clear fractions to get my coefficient equation, I'm going to have a bunch of different convenient x values that will just zero terms out, and the term that's not 0 I can solve for. So I'll do one with 3 factors, but it would be the same method, just a little more tedious if I had more than 3. But again, it would work the exact same way. For example, let's look at the integral of x squared over x plus 1, x minus 1, and x plus 4. So again, this is a proper rational function. The degree at the top is 2, degree at the bottom is 3, so therefore it's a proper rational function. Rational meaning top and bottom are polynomials. Proper because the degree on the top is smaller than the degree on the bottom. And it consists of non-repeated linear factors. So I don't have an x plus 4 squared. I don't have an x squared plus 1, which would make that a quadratic factor. Those will all be cases in subsequent videos. All right, so let's follow the same technique as the previous example, meaning we're going to start with the generic expansion. Okay. And again, going back to the very beginning of the video, to figure out what rational expressions we added to obtain this, what we do is we say, well, what were the possible denominators? Certainly I had to have a factor of x plus, or an expression whose denominator was each one of these. Okay? So that would give me an x plus 1, an x minus 1, and then an x plus 4. For the numerator, well, that's what we're going to solve for. In this case, we're going to have 3 unknown coefficients, a, b, and c. So there's my generic expansion. And then to get the coefficient equation, we're going to multiply both sides by this entire denominator. That gives me the following for my coefficient equation. X squared is equal to a, well, the x plus 1 will cancel, leaving the other 2 factors. For the b term, the x minus 1 would cancel, but we get the other 2 factors. And then plus c times the x plus 4 would cancel. again, leaving the other two factors. We'll then take this equation right here that I have in blue, and we'll solve for a, b, and c using, once again, convenient factors, or convenient choices of x. You notice that the convenient factors of x in this case will be x equal to positive 1, x equal to negative 1, and x equal to negative 4. Let's go through and choose each one of those. First and foremost, let x equal to 1. Plug it into both sides of the equation, in other words, everywhere where you see an x, and we would get, so 1 squared, meaning 1, is equal to, well, if I plug in x equal to 1, that's going to make this 0, so therefore the whole term is 0. If I plug in 1 here, that's going to make that whole term 0. Therefore, that would be b times 1 plus 1, which is 2, times 1 plus 4, which is 5. Therefore, the b value is 1/10. Next one, let x equal negative 1. On the left-hand side, negative 1 squared would be positive 1. And which terms go to 0? Well, negative 1 would make the b term 0. Negative 1 would make the c term 0. The only thing that's non-zero would be the a term. Negative 1 minus 1 would be negative 2. Negative 1 plus 3 would be positive 3. Therefore, a would be negative 1/6. Last convenient choice, let x equal negative 4. C is the value that we're still trying to find, and notice that C is the value that would be non-zero. So negative 4 here, negative 4 here would make the a and the b term 0. And again, plug it into both sides. Negative 4 squared would give you positive 16. Negative 4 plus 1 would be negative 3. Negative 4 minus 1 would be negative 4. Giving me C would be 16 over negative 12. Both of those have a factor of 4, so we can cancel that, giving negative 4/3 for the value of C. And then finally go back to the original question, and we were looking at the integral of x squared over x plus 1, x minus 1, x plus 4. We just showed that the integrand can be written as a value, which is negative 1/6 over x plus 1, and then the b value over x minus 1, that means 1/10 over x minus 1. And then the c value over x plus 4, giving me negative 4/3 over x plus 4. And each of those terms is simple to write the antiderivative for. Final answer would then be negative 1/6 natural log of x plus 1 in absolute value, plus 1/10. Natural log absolute value of x minus 1, minus 4/3. Natural log absolute value of x plus 4, plus c. Once again, if I had more than 3 factors, it's not more difficult, it's just more tedious. In subsequent videos, I'll go through what happens if I have repeated linear factors or non-irreducible quadratic factors, so on and so forth. So look out for those as they get posted here in the coming weeks. But thank you for watching, and don't forget to subscribe.